we have discussed about the plots of probability density for 1s and 2s orbitals. Now we will come to the conclusion that how the shape of the s orbital will look from these graphs. So, before discussing the actual shapes, we need to know certain things. That first of all, number of nodes in an orbital is given by n minus 1, where n is the principal quantum number. So, since in 1s we see that the probability density function doesn't reach 0 at any point. Now, if we calculate mathematically, then for 1s, number of nodes is equal to 1 minus 1, that is 0, which is evident from the graph as well. But in the graph of 2s, we see that the probability density function reaches 0 at one point, and mathematically for 2s, number of nodes will be 2 minus 1, that is 1. So, we get that there will be 1 node for 2s and 0 node for 1s. Now, there are two types of diagrams by which we predict the shape of orbitals. One is charge cloud diagram. It is expressed in the forms of dots, expressed as dots. Okay. So, in the charge cloud diagram, the density of finding an electron is expressed in terms of dots. So, the density is higher when the region is near the nucleus, and the density gradually decreases when we move away from the nucleus. For better understanding of the diagrams, that is the shape of the orbitals, there is another type of diagram called the boundary surface diagram. In that case, a contour of the orbital is plotted on a 2D plane. So, it is considered that the s orbital is spherical in nature, which is predicted from the charge cloud. So, in 2D, the s orbital is drawn as circle with its center on the nucleus, and we will predict the shapes of the s orbitals for different principal quantum numbers. The shape will remain the same, but the number of nodes will increase. So, how we will describe them in the form of diagrams? Boundary surface diagrams for s orbital. Let us see. So, in the charge cloud diagrams, the electron probability density is expressed as dots. In boundary surface diagram, the contour surface is drawn where the probability density is constant. In the charge cloud diagram, the density doesn't remain constant. probability density in this case, probability density gradually decreases away from the nucleus. But charge cloud diagram is not a very reliable method if we try to draw the shape of the orbitals, because we cannot exactly draw the shape of the orbitals in an understandable way when we are drawing with a dotted diagram. So, the boundary surface diagrams provide a relatively understandable diagram of the orbitals and they are somewhere accurate. So, for S orbitals, as a general consideration, it is considered as spheres. S orbitals are considered as spheres. So, in 2D, that is in a plane of paper, it is drawn as a circle. Whose center is on the nucleus. Okay. So, let's draw 1s. 1s is drawn like this. Okay. This is 1s. The center is the nucleus and the probability density of electrons is represented like this. Now we know that 1s has no node. So we can see that the probability density is constant around this circle. Now for 2s, we know that the number of nodes is 1. So there should be one region where electron probability density is 0, right? So 2s is drawn like this. So 2s is drawn like this. So the probability density is present here and in this region also, but this is the blank space, that is the node. So we have one node. Now if we draw 3s, then the number of nodes will be 2. Therefore, there will be two regions where psi squared is equal to 0. That is where the probability of finding an electron is 0. So, 3s is drawn somewhat like this. So these are the nodes. Okay. So roughly these are the diagrams how the s orbital is described in the form of circles. So as the principal quantum number increases, as n increases, number of nodes will increase. Okay. and the number of nodes is given by n minus 1. So, this is how the s orbitals are described. Now, in the boundary surface diagrams, which regions are expressed in boundary surface diagrams? Since we can see from the plots that it never touches 0, so it will continue up to infinity, but that is not possible to draw. So, how much we will draw? So, in the boundary surface diagrams, those regions are expressed which has a probability density of 90%. That is, the probability of finding an electron is 90%. So, a question may arise that why don't we draw a diagram which expresses 100% of probability density? Because that is not possible. Because as long as we are at a finite distance from the nucleus, there will be some amount of probability density left always. Because the plots we have seen that it never touches 0. So, at any finite distance, the probability density will never be 0. So, it is not possible to define a rigid surface in which the probability density is 100%, because we will not be able to cover 100% density with any rigid boundary. Therefore, in boundary surface diagrams, we have regions having 90% probability density. And what will be the size of the orbitals? Size of s orbitals increase with increase in n. That is, 1s is smaller than 2s, 2s is smaller than 3s, and so on. The shapes will remain same, but the size will increase. Shapes remain same. Okay. Now, we will see the shape of p orbital. Shape of p orbital. So, for p orbital, L is equal to 1. So, m will be -1, 0 and +1, and smallest n possible is 2. Therefore, 2p is the smallest p orbital. Okay. Now, since there are 3 p orbitals possible, so they are px, py and pz. These are along x, y and z axis respectively. And p orbitals have the shape of 2 lobes touching at the origin. Okay. This is also known as the dumbbell shape. Okay. So, we will draw the p orbitals. If these are the 3 axes, this is Px, that is along the x-axis. Along x-axis. Now this is Py along y-axis, and this is Pz along z-axis. Okay, so these are the three p orbitals, px, py and pz. They are along the three coordinate axes, and the two lobes touch at the origin. The origin represents the nucleus. So there is no electron density at the origin. Okay. So the origin is a point where there is no electron density. Now what are the nodes? So number of nodes. Now there two types of nodes are possible. One is radial node and one is angular node. For s orbital only one node was there, one type of node, but in case of p orbitals there can be two types of nodes. So angular nodes, what are angular nodes? That is, let's say Px is along x-axis, right? Px is along x-axis. So in yz plane there is no electron density. So yz plane is known as the angular node or nodal plane. Angular node is given by L and radial node is given by n minus L minus 1. So for 2p, L is equal to 1. So there is one angular node and n minus L minus 1 is equal to 0. So there is no radial node. But for 3p, angular node will be 1 and radial node will be 1. So there will be one node for 3p. So we can write total number of nodes as n minus L minus 1 plus L, that is n minus 1. So total nodes remain as n minus 1. Now all p orbitals have similar shape, size and energy, and they are perpendicular to each other. Okay, so they are perpendicular to each other. Now in the next part we will study about the shape of d orbitals. Thank you.